So it is a great pleasure to have you today with us, Brent Tully from the University of Hawaii. Well, having to say a few words about him, it's difficult what to pick. So I made a list, but it's too long. So probably the thing for which it's most famous, one of the is the Tully-Fisher relation that I'm sure everybody knows. But also has been working on almost everything, and it's so. It is really a great pleasure to hear about what is new about H-naught, because he has been working on the measure of the Hubble constant, starting from a value of 85 kilometers per second per megaparsec. And now this value is shrinking. And as you know, there is this tension between values from the distance ladder and values from the early universe. So I'm really glad to hear what he will tell us about this new measurement, the population to distance scale with HST and JWST.
Thanks, Sala. I have to apologize right in advance that my hearing is really going very badly. So if the acoustics aren't great here, and so if somebody asks me a question, I might ask you to talk into this microphone here, which will start my hearing. So I actually prepared this talk for a meeting in Portugal that was just a couple of weeks ago, and it was specifically about all the good things that were coming out of the Hubble Space Telescope and James Webb Space Telescope. And in particular, this is the program that we've been doing is very relevant to both those telescopes. So that was a convenient thing to a possibility to get a big presentation. Let's see if I've got control over this.
Sorry, try again.
Yeah, let's see. Okay. Yeah, okay, got control. So these are the people I've been working with on this project. And you'll see a little bit farther along with what each of these people are doing in the program. Oops, what did I do? Okay, so there's this population one ladder that Adam Rees has popularized as a route to get to Hubble constant, which involves then these steps where you've got a local calibration of the Cepheid relationship within the local group, and then you then transfer that over to supernova at distances that are close enough that you can see Cepheids in those galaxies that have had supernova go off in them. And then once you have a 0-point calibration of your supernova, then you can go out to large distances beyond any peculiar velocity contaminations to velocities, and end up getting the Hubble constant value that way. And he's got a number like 73, which, if you've been following the literature at all, you would have heard that this is in tension with the value of 67 that is coming from early universe observations of the microwave background and a model that of how the universe would have evolved since those early days. So that if this is true, well, so there's three possibilities. Two of them is that one or other of these observations is wrong, or that really there's some physics. Basically the model is wrong, and so the evolution of the universe is early times is different from the standard model. And of course, that would be very interesting. It says that we don't have a full grasp of physics. So that's the population one ladder, but and already it seems to be like at a 5 sigma tension, but which is really quite intriguing. But we need a confirmation from an alternate, totally alternate way of getting distances, and that's what we're going to talk about here. I can control this guy. What we're going to talk about is population 2 ladder, where the geometry calibrates TRGB instead of cepheid, but the TRGB then calibrates surface brightness fluctuations instead of supernova. And then we look at surface brightness fluctuation instances at large distances to get a Hubble constant from that. And each of these steps is totally independent of that other ladder because it's all population 2. So that's the game, entirely independent of the population 1 scale. And these are things that we can do beautifully with JWST, HST, and JWST, except for this first step. Oh, what did I do again? There's this other button down here that I touch. I have fat fingers, God. Okay. So the whole concept then of the tip of the red giant branch as a way of getting distances. Okay, here I've shown you a color magnitude diagram that comes from Hubble Space Telescope observations of, in this case, the Phoenix dwarf galaxy. And the red giant branch then goes up to the tip of the red giant branch. Another feature that's obvious here, or evident that's important to us, is the horizontal branch where you have RR Lyrae stars. So these are the kind of things that we want to calibrate to go up the ladder. Here's some examples of Hubble Space Telescope color magnitude diagrams of galaxies in the lone group. And this is not a complete sample, but just to show you the sorts of data that Hubble Space Telescope was getting. And you can see that in all of these cases, the most obvious feature in all of these color magnitude diagrams is the red giant branch. And that the tip of the red giant branch then is pretty evident just by eye looking at all of these color magnitude diagrams. And here is an example of observations with James Webb Space Telescope of the WLM galaxy. And again, you can see the red giant branch going up to the tip. You can see the horizontal branch, red clump, and main sequence, and all these other features of color magnitude diagram that we're familiar with. And with James Webb already, there are observations being made of all of these cases I'm showing on the left. These are all local group galaxies. And so come back in another year or so, and we're going to have color magnitude diagrams of equivalent quality, as you see here for WLM. And okay, and then the other thing that we're going to, well, then the issue is calibrating the TRGB. And that's really why I'm here to talk to Sala and other people, because this is actually something that the calibration is something that's got to be done locally using Gaia, using information, say, about the RR Lyrae stars that are going to be found in here, and then calibrating the tip of the red giant branch in all of these local group galaxies. So we're going to have quite a bit of redundancy, but it then is a case of using Gaia information to make this calibration. Okay, going onward then. Another very important step in the ladder has been this remarkable situation in the NGC 4258 at about 7 megaparsecs, 7.5 megaparsecs, where there's a phasor system in this galaxy it's totally fortuitous because there's no second case within any reasonable distance. But here's a case of this galaxy that's almost edge on, and it's got all these masers that are in the nuclear region that are being useful to give a geometric distance to this galaxy. And you see, well, with many decimal places, the value that people are coming up with for this geometric distance to this NGC 4258. Now, so I call it a Rosetta Stone because there's a whole bunch of ways of using that. For example, there are cepheids. So Adam Rees and his gang have been have these observations that we see in these. These are the JWST positions of the camera, and you can see that in this central region, he's measuring cepheids that we're seeing in his color magnitude diagram over here. And in these outer regions, we pick up tip of the red giant branch distances. So here's the color magnitude diagram restricted to these outermost regions where we get a good measure of the tip of the red giant branch. And here's where cepheids lie in the inner part and get this beautiful cepheid period luminosity relationship. So all of these things are coming together with this one galaxy and assuming for the moment here, this maser distance to NGC 4258. So this is then, so for right away, if we knew the distance to the WLM, for example, we would then have a direct handle on the distance to 4258 as an alternative. So in other words, just this distance, the difference between that measurement with James Webb and the tip here for 4258, I just put this in my eye. But if you did this and you looked at the difference then, taking into account small reddening differences, then you can see that this would be the difference in modulus between this local group galaxy and that one there. So if you had the distance to this local group galaxy or any of those other ones I talked about, then you would be able to then make a separate measurement, which you could then compare with this maser distance, just to see that we're all on the same page. Now, this is a bit of information here that came to me relatively recent. Richard Anderson is the lead author on this, and this is using this oval observations of variable stars in the LMC. And it's turned out that tip of the red giant branch stars are variable. And indeed all, well, as stars approach the tip, they become variable, and AGB stars above the tip, they're variable too. And it turns out that there's complexity to this. That is to say that if you look at them, you find that there's a split period luminosity relationship. This is luminosity here, and this is period. And when you look at stars that are at the near the tip, you find that they follow either one or other of these two families here. And indeed, these colors here are ages. And you find then that the sequence A, the median ages of those are about 4 gigayears, whereas the sequence B are more like 7 gigayears. So there's a lot of interesting physics going on here, which remains to be seen. But at any rate, assuming the distance to the LMC as given by eclipsing binaries, then we get this calibration here for the tip of the red giant branch in the HST filter for F814. And that gives us a distance right away to 4258, which is within 1.5% of the maser distance. So all of this is to say that there's a lot of different ways we're working on to get all of this jigsaw puzzle put together here. And it is still a work in progress. But anyway, if we then accept that we're going to, not quite there yet, but we're going to have this geometric calibration of the TRGB, and we're pretty close. It doesn't seem to have too much slop in it. Then we have this calibration of TRGB, and going onward then to this next step. Here now we've got a program in cycle 2 of JWST to look at 14 galaxies nearby, rich elliptical galaxies, where we can see TRGB and we can calibrate surface brightness fluctuation. These are the first 3 to come in, and they're all in the Fornax cluster. And just giving attention then to the TRGB aspect, you see these splits here. So these 3 galaxies, we look separately at different panels of the camera, and to see consistency across the different parts of the camera. And we get these different distances that you can see here, and roughly a distance here of 19 megaparsecs for Fornax, and the dispersion here of 1 megaparsec is about the dimensions in the line of sight of the Fornax cluster. So this error of 0.7 is about consistent with the depth of the cluster. And the point to be really made is how excellent this data is. I jumped too much. This is one of those cases. This is NGC 1380, one of the cases. And what I believe I've blown up over here, just this part of the diagram here, just taking it over here. And what I want to show you there, though, is this is plus minus 5%. These red dashed curves here are plus minus 5% over this fit here. And 5%, you can see by eye. Now we do a maximum likelihood procedure to define the tip and where we put in synthetic stars and recover them with varying magnitude and color. So we do things a lot more formally, but I'm saying to you, as you look here with your eye, you can easily get a relative distance here of 5%. In fact, probably 2 or 3%, just looking at that, right? And how well that is. So this is why this method is so good. Here's just a comparison then of now looking at 4258. If we believe the maser distance and we take the fit for 1380, then you can see then that the difference between those 2 galaxies is this 1.99, call it 2 magnitudes, or a factor of 2.5 in distance. Okay. So a very nice aspect then of the NIRCam camera on JWST is it's got these two different panels. And for us, that's great because what we can do is set one of the panels on the center of the galaxy where there's high surface brightness, the stars are high metallicity, and we can measure in an appropriate way the surface brightness fluctuations. Way over here on the outer part, where you don't see much over here, you're looking in the halo of the same galaxy, where the stars are far enough apart that we see individual stars and they're low metallicity. There are lots of low metallicity. There's also some high metallicity, but lots of low metallicity stars, and we can measure the TRGB very well. So this is great because one single observation, we at the same filters, we can see the TRGB and the surface brightness fluctuation. And just to remind you, the surface brightness fluctuation is intrinsically the same mechanism as we're using in TRGB. In other words, we're looking at the fluctuations in the brightest stars, which in a metal-rich old age are mainly the stars in the upper red giant branch. So it's the same physical mechanism. If we understand TRGB, we understand SBF. We make the measurements simultaneously. And here, for example, is the power spectrum that we see for NGC 1399 as a case in point. And the amplitude and of the power spectrum is going to give the distance because so this surface brightness fluctuation methodology works on a measure of the fluctuation such that nearby there's large fluctuations because we're semi-resolving the galaxy, and as you go farther away, the fluctuations are damped as a square of the distance. So we now have then, well, it's a work in progress, but we will then have a good transfer of the TRGB 0 point over to the surface brightness fluctuation 0 point. As I say, we've got 14 galaxies on our program. 3 are in, and in fact, 2 more are coming in these very days. We're starting to get observations in the Virgo cluster, but we haven't got those yet. But we will, by the end of this cycle, have the information we need to have a good transfer of TRGB-SBF. Now, here's another aspect of the issue. This is going back to Hubble Space Telescope. The Hubble Space Telescope, one of the very nice things that was done in the past was observations of surface brightness fluctuations in the Virgo cluster and the Fornax cluster, which you're seeing here. And the Fornax cluster is slightly farther away, and so this scale. The scale up the side here is a measure of the fluctuation spectrum, and there's a color dependency. And so here's Fornax cluster, which is slightly farther away, and so in the way of astronomers, it's a larger number in this magnitude scale. But if you shift the two of them onto each other with this distance difference, you get this scaling here for the dependence on color. And then if we then take this maser distance to NGC 4258, that transfers over to the Fornax cluster in the ways I just showed you, just with 3 objects. But then using this scaling, we would anticipate that the Virgo clusters at about 16 megaparsecs. Well, we'll find out because we're going to have a half a dozen observations directly in Virgo, but those are just coming in. But this is to show you what has been done with HST and using this color relationship. Now we need something similar though for James Webb. It'll be quite similar because the filters are quite close. In the case of HST, we're using this F8 815W, and in the case of JWST, we're using an 090. So there's one is at about centered about 800 microns, the other is at 900 microns. This is a sweet spot where there's not too much metallicity dependency in the tip of the red giant branch. Here's then what we've done with surface brightness fluctuation with Hubble Space Telescope. Now the scaling here, the 0 point, is set really by in the old days with cepheids and 4258 and the large magellanic clouds. But this 0 point is not yet the new 0 point that we evolved with population 2. This is using a population 1 0 point on this, but that's what we see right now. And again, it's in this particular case, it's got 63 galaxies defining this, but we've got another 58 galaxies already from a SNAP proposal from HST that is being reduced. And that was in cycle 28 and cycle 31, which is the current cycle. We have a SNAP proposal, which is now bringing in new observations. We've got about 15 or so far. And then there's 29 galaxies from another program that some of these people have been involved with. So at the end of this, we'll have of order 200 surface brightness fluctuation measures out to about 100 megaparsecs. That's about the distance of the coma cluster. So that's already a pretty interesting distance. There are issues of peculiar velocities in here. We would like to go farther, but this is already a pretty good start. But we want to go a little bit farther. Here's another program then. And this is an important program that we've just got cycle 3 time for. Where we're looking at 40 galaxies, about 40 galaxies in the coma cluster. This little panel in blue shows the distribution of the sources in the coma cluster. And the whole point of this is to again get the equivalent of this plot here in JWST bands. This is in HST bands. And JWST bands will be close, but it'll be slightly different. And so we need this calibration using these 40 galaxies in coma, which are all essentially the same distance within 1.5% distance. And we will then have a relationship that looks like this in the JWST bands. And that will then complete the calibration, if you like, from tip to brightness fluctuations with a calibration of colors. And so then the final step of the game, which remains, is then to go to the far field with JWST out to a redshift of about 0.07 or so, which should be well beyond peculiar velocities. Influence of peculiar velocities. And that gets us to this. Basically, it's completing. So we get the 0 point link through TRGB, which we've got through this cycle 2 observations, 16 galaxies, where we simultaneously see TRGB and SBF. We calibrate the metallicity age dependencies with this cycle 3 proposal with looking at 39 or 40 galaxies in the coma cluster, which are all at the same distance. And then remaining to be done, we don't have this time, but we'll put in proposals and hopefully we or somebody else will look at surface brightness fluctuation observations of galaxies out to redshifts of 0.07 or so with James Webb, all with the same filters. And that will then give us this completed site. Well, then we need, of course, the 0-point calibration from whatever Gaia gives us, or whatever we did get for the nearest galaxies, the 0-point on TRGB. But that will then give us a population 2 a procedure over the population 1 that exists right now. And it will be better. It will be better. Why? First of all, we don't really understand supernova very well. I mean, we do not know how all the different ways that you can have a supernova and what how they change. For example, presently the supernova that are being used by Adam Rees are supernova that occur in late type galaxies, because that's where they can find cepheids. They don't have any early type cases. The other thing to remember with supernova is they're all over the sky, north and south, or spring and fall, different observers using different filters and different methodologies, different fitting functions. And I've been involved in a process out in Hawaii, and I don't know that you can do better than 7%, unless you really have a lot more information. I mean, if you have very detailed time and spectral information, maybe you could do a bit better than 7, but I haven't seen it yet in a general survey. But I think we can get 5% with JWST and surface brightness fluctuation. And here's the critical thing. We're using the same filters all over the sky and at all different depths. And this is something we're not doing with supernova. So it's the same procedure in all sectors of the sky. So that's going to give us a more reliable result. And so I'm saying this, come back in a few years and this population 2 methodology will be the way to get H0. So that's my message. We aren't there yet.
Thank you, Brent, for this very